Welcome to this tutorial session on the oscillator's role on synchronization. Along with the oscillator fundamentals, we will see the role of oscillators in synchronization systems and the key parameters to look for when selecting the oscillators. Telecom synchronization in general is hierarchical. In this example of a cellular network, the end nodes have certain synchronization requirements. The timing flows from the source to the radios through the core and backhaul networks. Each network element has an equipment clock function that receives synchronization from the upper hierarchy, cleanses it, and steers it downstream. At the final node, the local clock is prepared for the end application's requirements. Residing at the heart of each equipment clock is a local oscillator that provides ticks at regular intervals. The crux of synchronization is to match these ticks with that of the source clock at each network element. The frequency spectrum reveals the stability of the oscillator. The expectation in frequency domain is a single line that corresponds to the frequency of oscillation, but in reality, there is a spectrum of frequencies. Depending on the quality factor of the resonating element that is used to build the oscillator, the peak and the spread can vary. Quartz crystals are known for high quality factor, producing very clean clocks. Quartz material exhibits piezoelectric behavior. When electricity is applied, quartz is mechanically deformed. When removed, it not only comes back to the original shape but also produces electricity. This tank circuit behavior applied to an electronic circuit produces alternating states. To build oscillators, along with the RC, LC, ceramic, dielectric, and other type of resonating elements such as micro electromechanical structures, better known as MEMS, are also used. Silicon based and quartz based MEMS resonators are also used in the oscillators. Quartz is grown in autoclaves from the quartz seed materials under the influence of temperature and pressure. Quartz bars are cut to make wafers from which the blanks are made. Electrodes are attached to the blanks to build them onto resonators. Electronic circuits are built around the resonator and packaged to form the final oscillator. Now, let's look at the major contributors to oscillator frequency instabilities. Amongst them, the systematic variation that happens over a period of time is called aging. Temperature has an impact on frequency accuracy, short to medium term. Vibration has an impact, and so is shock. Storing the oscillators for a long period of time, switching it on and off, approaching it a point in temperature from higher or lower temperatures all causes frequency instabilities in oscillators. Managing the impact of temperature on resonator improves the oscillator stability. There are several techniques that are used to approach this problem, resulting in different stability categories in oscillators. A typical crystal oscillator has several tens of parts per million in frequency variation across the temperature range. A temperature compensated oscillator, better known as TCXO, dynamically reads the ambient temperature and applies predefined compensation to reduce frequency variation to few hundreds of parts per billion. The oven controlled crystal oscillators, known as OCXOs, heat the resonators outside the operating range of the oscillator to minimize the impact of temperature. In this way, the instability is further reduced to few parts per billion or even less. New techniques, a combination of the two, commonly referred to as a hybrid TCXO, applies the ovenizing technique combined with compensation. There are a number of key aspects on the selection of reference clocks. Free run accuracy refers to the clock accuracy when an oscillator starts up. In order to be able to lock to an upstream clock and to provide downstream clocks within a certain accuracy, the oscillators are to be within certain accuracy. The dynamic performance of an oscillator is a measure of noise contribution to the servo system output in the synchronization process. The error contribution is primarily from the temperature sensitivity of the clock oscillator. Holdover is the ability of the oscillator to keep the system accuracy within certain limits when all the synchronization sources are lost. Depending on the duration of holdover, the temperature sensitivity and the aging contributes to this instability. The unwanted frequency components of the clock contributes to phase noise and jitter. Wired transmission networks primarily uses level triggered detection probabilities, and variation of the clock or jitter has an impact on the bit error rate. The quadrature amplitude modulation systems, which are commonly used in wireless networks, the phase noise on various frequency offsets are critical. In order to understand the dynamic performance and the impact on noise generation, we can consider the following example. The servo system shows that the corrections to the output becomes faster as the loop bandwidth is increased. When the loop bandwidth is decreased, the correction rate slows down and the impact of the oscillator variations between the correction intervals starts to appear at the system output. The temperature versus frequency response curve shows an oscillator frequency variation with high temperature sensitivity. With the servo correction intervals spaced across certain time periods, results in certain types of output error. In the second graph, as the temperature sensitivity of the oscillator is significantly smaller, the corresponding output error is also smaller. As seen in the third graph, the same effect can be achieved by increasing the loop bandwidth, thus reducing the distance between the correction intervals. Synchronization holdover happens when the reference is lost. A state-of-the-art synchronization system usually uses GNSS, packet-based, and physical layer-based reference clocks. Holdover reference can relate to packet layer assisted holdover, which happens when primary clock to the system, which is in general a GNSS based clock, is lost. A physical layer assisted holdover is when the packet layer is also lost. Finally, the system turns into oscillator based holdover when all the references are lost. Phase holdover is important with the latest cellular network technologies. In a holdover scenario, the initial frequency and phase error of the system is contributed by the servo. All the other effects of holdover comes from the instability of the oscillator. The temperature ramp size and rate, the aging rate, the microjumps in frequency, impact of direction of temperature movement on frequency called hysteresis, all contributes to frequency errors resulting in the accumulation of phase error. The impact of temperature is worst. In this example graphs below, the holdover starts at time 0 and the temperature variation happens in the middle, at the beginning, and symmetrically. The phase error is worst when the temperature variation happens coinciding the entry to holdover. In the symmetrical variation situation, the phase variation is minimal. The constellation points in quadrature amplitude modulation systems are to be clean in order to improve the detection accuracy. The phase noise on the clock rotates the constellation points, thus adding to the error vector magnitude of the system. Most of the wireless systems use QAM-based modulation. Wired systems traditionally used amplitude level based decision methods, and thus the clean eye diagrams are important for better decision margins and low bit errors. Clocks with less jitter drives eye diagrams with good height and width. Systems perform a jitter or phase noise cleaning on the network recovered clocks to make them suitable for the end application. To summarize this session, oscillators are the fundamental building blocks of all the clocks. Temperature compensation and event control methods are two commonly
used methods to mitigate the impact of temperature and to improve the stability of the clocks. In many applications, the loop bandwidth and the required output level stability will determine the type of oscillators that are needed to be used in the application. Freerun, water generation, and holdover are the key aspects of the oscillator selection. Depending on the requirement of the physical layer, jitter and phase noise may also be considered. Thank you very much.